So, hi everyone. I'm gonna talk about the magic of music matching for the third time today because I'm screen recording, and if my face looks a bit angry, it's because this is the third attempt. The first one, my neighbor decided to cut tiles outside, which messed up the audio completely. The second time, my laptop ran out of hard drive space, so I really hate recording a webcast. I love to be on the cruise with you guys. Sadly, it was cancelled. I was unable to travel. Stupid coronavirus. But please, it's not your fault. I just hate recording. I just hate talking to a screen. And this is the third attempt, and I really hope this goes well because I'm not looking forward to doing this presentation for a fourth time. Please. So bear with me. My name, Roy van Rijn. I'm a Java champion, Groundbreaker ambassador, and I'm the founder and leader of the Rotterdam Java user group. I work for a company called Open Value, and I'm running the Rotterdam branch. The best one, obviously. No, just kidding. And you can follow me on Twitter. Just go to this Twitter handle or read my blog on my website. So, why are you guys programming? Guys and girls, sorry. Why are you people programming? For me, it was to play games. The best way to get games when I first had that PC was to get a book like this. And these books were in my local library, and I could just go there, and these books had pages filled with source code. You could just copy paste the source code. You actually have to type everything into the terminal without line numbers, without an IDE, without anything that's helping you. No typos whatsoever. And when everything was done, you could run the interpreter and you could play a game. And this made me understand how it all works. Well, not all, but it made me understand how programs work, what kind of stuff goes into it. Whenever I missed a character somewhere, it would show me. And yeah. So this for me demystified a little bit what software actually does and what you could do with it. But for me, software has these magical moments. So one of these magical moments was when I first got a computer, everything was text and console based. You just had 80 characters and that's it. And then I went to images. Suddenly you had logos and photos, and you could actually, you have a UI, you could see stuff. This was magical. I had no idea how you would program something that would draw an image. So another thing was the first time I navigated a 3D world. I had no idea how you could possibly program something like Wolfenstein or Quake, where you could just walk around, look around. Mind-blowing. The first time my computer spoke to me. So early games had these bleeps, and then I got a sound card and it had songs, and then suddenly it said stuff to me in a human voice. I couldn't understand how a computer was able to do that. Another magical thing was OCR. You gave it a picture, and from that, magically, it deducted that there are some characters, and it would turn it into text that you could edit and copy paste. And I knew how to program. I had no idea how you would make an OCR program. Or voice recognition, for example. Sure, the early voice recognition applications were complete and utter crap. Only the last couple of years it became kind of usable. But I had no idea how you would make something like that. Another thing was Google Earth. The first time I saw my own house in a satellite image, you could basically watch the entire Earth. Yeah, it was magical. So some of these moments I never forget. And the same thing happened when I first used or heard about Shazam and SoundHound. So, story. This all happened in the summer of 2010, somewhere in Maasluis, which we are currently looking at. I still live there, or actually I live there again now. And I was having a beer with my friends. One of my friends walked up to me and said, "Hey Roy, look at this app." He pulled out his phone and he starts Shazam, and he holds his phone up in the air. The phone listens for a while, and suddenly it tells me the name of the song. And my mind is completely blown. how does it do that? How does a app listen, deduct which song it could be, and tell me which? Mind-blowing. I had no idea. So the next morning, when I finally woke up with a bit of a hangover, I have to know how this works. That's the first thing that came up. I have to know. This weekend, I have nothing to do. My goal for this weekend, I have to know how Shazam works. So I do what every good developer does. I Google, how, with Java, do I listen to a microphone? And it turns out this is actually pretty easy to do. There is an audio system in Java which you can just access, and you can get access to a microphone. So if you want to code this, the first thing you need to do is define an audio format. And in this audio format, we put a couple of things. So we put a certain sample rate, a sample size in bits. It's a microphone, which is a single channel, so we have one channel. The data is signed, and it's in big endian format. And this audio format works for almost all microphones. And with this audio format, we can define something that's called a data line, or a target data line. And then, the most important thing is we access the audio system, and then we call getLine. This gives us a line we can open and start, and it has a small buffer. So everything that comes into your microphone is put in this small buffer, and we can actually get it. We can actually read from this target data line, and we need to do this quickly, because if we don't do this quickly enough, the small internal buffer will overflow and we will lose information from the microphone. So in a small separate thread, I'm defining a small 8K buffer. I'm defining a huge output stream, which will contain eventually all our microphone data. And I'm starting a small infinite loop, or close to infinite. And this loop is constantly reading from the target data line and putting everything in the byte array output stream. So it's just quickly flushing everything into the byte array we are storing our microphone data. And this is enough. This is enough in Java to, in the background, just listen to the microphone and store all the data. So, a couple of hours into my Saturday, and I'm like, yeah, I'm almost halfway there. I'm nailing this. I'm already, I've got an app, and it's starting, and it's listening to the microphone, and I'm almost there. I just need to do the matching part now. But then I came to think, what's actually in this data? What does a microphone give us? So I decided to print out the data that was in the byte array, and I saw something like this. And I'm like, wait a minute, what is this? What am I looking at? What does a microphone do? What kind of data does it give me? I had no idea. So I opened up Excel or OpenOffice, and I decided to plot it in a graph. And then I noticed something, yeah, this looks familiar. If you've ever used an audio editor, this is what audio looks like. So when I was silent, the line was almost flat, and when I made it a sound, when I was clapping, the waves started to appear. So yeah, this is audio. But then I realized it was time for some biology and physics, because what does this all mean? What does sound, what do these numbers mean? Basically, sound is pressure. When I clap my hands, the air molecules get pushed away, and this wave is propagated through all the other air molecules until it hits your eardrum. And your eardrum is moving with this wave, with this pressure, and your brain interprets this as sound. Turns out the microphone is exactly the same. It also has a small membrane in it, which is vibrating when there's pressure. So now we can also understand what the sample rate and the sample size does. The sample rate is just how often does the microphone record its position. Is it pushed this way or this way? And the sample size in bits says something about the precision. So how precise is the measurement of the thing that's being moved? So we can do two things to increase the quality of what we are recording. We can do more measurements, increase the sample rate, or we can improve the accuracy of what we are measuring. So these are all kinds of things you can play with when you record sound, basically anywhere, but in Java. Turns out though, these positions are kind of useless. Because sure, our ear detects these waves and it detects where the membrane in our ear is, but that's not very useful because our head hears something differently. Our head hears, our brain detects frequencies. So for example, if you have a single wave, a single frequency, this is a low frequency, like our head hears just this one frequency. Our head does not hear something that's moving up and down. But what we record is a signal going up and down. If we have like a higher frequency, the wave gets shorter, and this is a higher frequency. And it gets even more complicated if we start to combine two waves. For example, this low frequency and this high frequency combined does something very weird to the wave. But what we hear, what our brain interprets, is just two distinct frequencies. It turns out though, you can turn the upper image into the lower image. And you can do this using something that's called the Fourier Transformation. You've probably heard about the Fourier Transformation, but in the coming slides, I'm actually going to explain how this Fourier Transformation kind of works. So Stuart Riffle, he blogged on an old website, which is no longer online. I couldn't find any copy of it, on how this Fourier transformation works. And he explained it in an excellent way. And I'm just going to repeat what he blogged on his website. Imagine you have a certain recording. So this wave is going in a weird pattern. And basically what's happening, and I'm going to use my little remote control prop here. What's happening is the wave's going up and down, and we are drawing it like this. So we are moving our imaginary stick amongst the x-axis. That's how we draw this wave. But in a Fourier transformation, we are not going to do this. We are going to do this. We are going to rotate at a certain frequency, that's important here, at a certain frequency, our stick. And we're going to draw our signal. So what happens if you take this audio format and we draw it, we rotate this axis, I don't know, let's say 10 Hertz. You get a pattern like this, all kinds of circles. And these circles are around the center point, because we are rotating around the center point, and yeah, that's what happens. But now let's look at the same graph, but now we're rotating at 3 Hertz, a different speed, and this happens. Now we get ellipses, and we're being pulled off center. And this is important because let's calculate the average. The average is now no longer in the middle, but we are getting pulled off center. And why does this happen? Well, for example, if you have a single wave that's going at a certain frequency, and we are rotating around in that same frequency, you get a peak that's always on the same side. So if you rotate and you record the average, and the average is being pulled off center, the further it's being pulled off center, the further this signal is actually present in the recording. So if we take the same recording and we would remove the 3 Hertz signal entirely, this happens. Now it's all based around the center again, because the 3 Hertz frequency is no longer in the original sample. Imagine you do this for all the frequencies there are, and you measure how far the average is. And it turns out this is all the Fourier transformation does. So this is the mathematical formula, and you can actually see what we just noticed in the formula. So x is the energy we want at a particular frequency. We have to spin, which is e to the I, that's spin. Your signal, which is xn, around a circle, 2 pi. at a particular frequency and average a bunch of points among that path. So basically the same thing we just said is in the mathematical formula, and you can actually see it. Excellent explanation on the Fourier transformation. That being said though, now I kind of understand how it works. I'm still too dumb to implement this, but luckily there's Commons Math. So we don't have to, we can just call Commons Math and it does the Fourier transformation for us. There is one huge cost though, because if we do the Fourier transformation, we lose time entirely. If you have a 3 or 4 minute recording and you do the Fourier transformation on this 3-minute recording, you will lose everything. You get the frequencies, but you will get all the frequencies that are present in the 3-minute recording at the same time. It's like the entire band playing all the notes and all the instruments at the same time for 3 minutes. Like they do this for every note that's in the song. That's not very useful because that just makes a lot of noise and there are a lot of frequencies and it's very hard. You cannot say which song it is. Like we need something that we need the time. We need to know when a particular note is being played and when the drum is being hit. So later that day, I'm getting a bit depressed. I'm looking out of the window. I'm like, yeah, I had these waves in time domain. Now I have the frequencies and I've lost track of time completely. How do I combine this? And then it suddenly hit me because looking out of the window is actually the solution because we can do a trick that's called windowing. We take the entire song and we just look at the first part. And in this first part, we do the Fourier transformation. And then we shift the window and we do a Fourier transformation again. And then we shift the window and we do the Fourier transformation again. Now we do lose a little bit of time information because we don't know where in this small window certain frequencies are being played, but we do know that we do have a window in which it happens. So how do you program this? Well, first I take everything out of the byte array, then I cut it into fixed pieces, and then for each piece I do the Fourier transformation. Later I updated it a little bit because you can do it even better. You can also program it to have a sliding window. So instead of moving an entire slice at a time, you can just slide it a little bit, do the Fourier transformation, slide it a little bit again, do the Fourier transformation, slide it a little bit again, and do the Fourier transformation. If you do it this way, you get even more frequency information because you can use a larger window, and you have more time information because you're slowly moving, not moving the entire thing at the same time. Quick question. Does anyone know what this is? Well, you can shout and show your hands, but this is a screen recording, so I'll just spoil it. It also says it in the picture here, but it's a spectrum analyzer. It turns out what we've just created in Java is a spectrum analyzer. If you take these windows, these small pieces of Fourier transformed data, we have the frequencies. If we will plot it to have the low frequencies in the bottom and the high frequencies in the top, and then just put each slice after each other as an image, you get something that looks like this. This is actually a recording of Aphex Twin. Aphex Twin is a DJ and he makes music or music. This song is not really music, it's some, I don't know, fancy noise. But what he likes to do is put spectral images inside his music. So this YouTube user used a very advanced spectrum analyzer to listen to the song. So let's just listen to the song. Yeah, that's something. Not sure if it's music, but you can clearly see there's a human head inside the song. And for me, this was like the perfect test case. I knew this existed, so I looked it up on YouTube, and sure, I programmed this. This is the same thing as we had before. I listened to the microphone, and for each row of pixels, in the bottom, the darker are lower frequencies, in the bottom is low frequencies, and top is high frequencies, and the brighter the blue, the more present that signal is. And as you can see, it kind of resembles the image above. So the spectrum analyzer used in the top, much better. My Java code, pretty crappy, but you can see the lines and you can kind of see the outline of the face. And I'm pretty sure if I used the right logarithmic scale and I programmed it a little bit better, I could get pretty close to the image they had there. But this told me my code was working-ish. So, with the hangover and the entire day of learning new stuff, by the time it was a 10:15, time for a recap. I was going to bed. Sound is just pressure and vibrations. Microphones and ears are pretty damn similar. Recording sound in Java is easy. There is a problem with the time and the frequency domain. You can transform between these two with the fast Fourier transformation. And we can use windowing to get some time information back. And if you combine everything, you'll end up with a spectrum analyzer. It's not Shazam, but we did build a spectrum analyzer the first day. So, the next morning I continued. It's my Sunday. I didn't have kids back then. I had the entire weekend for myself. So, what we need to do now is fingerprinting. I used the spectrum analyzer of the day before, and I used the song from Queen called Under Pressure. And I recorded it, and this is what it looks like. And then I recorded it a second time, and this is what it looked like. I've kind of aligned these things, but you can clearly see the images look very similar. So if we want to match a certain song, all we need to do is make sure these images are similar. So what do? I decided to take this recording and cut it into some bands, like low frequency bands, middle frequencies, high frequencies. And for each slice, I pick the loudest point in this frequency band. So I get a couple of points. And I did the recording again. So these are two recordings, and now you can see the red dots, which are just in these 8 bands, the highest frequencies. And if we would overlap these, you can clearly see, well, you can see that they are similar. This can be useful to actually match. So the samples aren't the same, but yeah, you get the point. So I take this single slice of frequency with the dots, and it has a lot of frequencies in it. But I just pick the loudest frequencies in the 8 bands, and then I compress everything down to just 46 different values. And these are stored as bits in a single long. So this is very efficient. A single long can store by slice fingerprint. And this is what it looks like. So you can see at the top we have these 4 single bits, and these are these 4 red dots. These are now in the 4 bits here. And then we have the 2 and the 2. And so if we do this for the entire song is just now a list of longs. And I want to do this for every song that's in my MP3 library. So it was 11 o'clock and I want to create a library of these fingerprints. To do this, we need to process MP3 files. And this can't be done out of the box with a Java audio system. You need a couple of libraries, and I ended up using JLayer, which is a real-time MP3 decoder, MP3 SPI, which is a Java plugin based on JLayer, and finally Tritonus, which is an implementation of the Java Sound API for these plugins. This is the code I wrote 10 years ago. It's a recursive function. We start with a root directory, then we get everything that's in the directory. If it ends with an MP3 file, we process this audio file, and then we do the same thing as we do with the microphone. We put everything into these fingerprint longs, and I store it somewhere. And if it's a directory, we recurse. Like I said, that was 10 years ago. Today I would do this completely differently, because now we have the new IO library, and we can just do files.walk with a certain path. We filter all the files, and if the file ends with MP3, we capture the audio. So yeah, going from this to this, much better. The whole lambdas makes it so much easier to have a good API to process files. So what did I have at the moment 10 years ago? I had a library of 3,000 songs turned into these fingerprints. I had a method to capture these fingerprints from my microphone, which I made yesterday. The only thing we need to do now is match. So we need to match something that's captured with the microphone to these songs in the database. So a fragment would look like something like this. So we have all these longs, and we have we just have a series of longs, which is our fingerprint. And the powerful algorithm behind, for example, stuff that Shazam does, SoundHound does, and my thing does, is that we can basically do a hash lookup for each and every row. And the hash lookups are very fast. So I take this single slice, and now I record all the songs that have this slice as well. And I also record the offset. So if we have enough matches for a particular song, we can just call it a match. And this is very cool, especially when you use the offset, because then you can say, I'm pretty sure we have a match for this song, and it's actually matching 1 minute and 20 seconds into this song. So this is very powerful. At that point, just in time for dinner, I had a working Shazam clone. Let's see a demo of this. So, time for a little demo. I've started my small application here, and as you can see right about here, 483 songs are being loaded into the database, because I no longer have a couple of thousands of MP3 files, because I now have Spotify. On Spotify, I've opened a playlist with 500 greatest songs, which should overlap the 483 songs that are there. And normally I would ask a volunteer to come up on stage, open his or her phone, and play this, shuffle this playlist. But right now I'm gonna demo because there's nobody here. So I'll just shuffle this playlist, and let's see if my computer can recognize the song. Pray for the good demo god. That's the first match. Next song. Oh, it's having a hard time. Ah, a new match. Next. Yep. Yep. Oh, that was a quick one. Humans will be faster with this. This is recognizable. Yep. Cool. Boat's having a hard time.
I may not always love you, but long as there are stars above you, you never.
Let's try another one. Oh, maybe we broke it. Surely you will recognize Bob Dylan.
Early one morning the sun was shining. I was laying in bed.
Yep.
Wondering.
Yep. Last one.
When I was a little girl, I had a rag doll. It was the only doll that I've ever owned.
Come on.
Now I love you just the way I love that rag doll. But only time I love.
We should end on a high though. Yeah. That was a quick one. So as you can see, it's most of the time able to guess the song, and if I would refine the code, it will probably work a bit better. I hadn't touched this code in 10 years, and I quickly made the demo up and running again before I could travel to Copenhagen, but hey. Another thing we can do, instead of just matching the song, in the second demo, I've actually I've taken the entire audio from the movie Rush and I indexed everything. So when I start the demo, right now the movie Rush, it's listening for that particular movie, but it's not only trying to detect that it actually hears the movie, but it's also trying to detect where in the movie we are. So I've now opened up YouTube, and there are a lot of clips from that movie. And I'll just randomly select one of the clips, and my laptop will listen. And if it finds a match, it will start the audio at exactly that time. So then I can stop my phone, and the audio will continue playing on my laptop. It will be synchronized, which is pretty cool. Let's hope it works. So let's just pick this scene.
Je wilt
and
sterkere tanden en gezonder tandvlees?
Commercial.
Listerine Total Care met 6-in-1 effect. Vermindert
That's the
tandplak,
demo effect.
beschermt tandvlees, helpt bacteriën bestrijden
Brush
en
your
nog
teeth,
veel
people.
meer. Listerine Total Care met 6-in-1 effect. Overtuig jezelf.
So let's skip somewhere in the middle.
There is Nicky Lauda, and on row 3 of the grid, Jody Scheckter from SoundHound in the
Now I can stop this one
Behind him, the rest of the 20
because my computer analyzed the audio and it found a match in 1 hour and 34 minutes into the song, into the audio track. So and then yeah, let's do it again with a different movie piece. So.
Oh,
Wir können auch Deutsch sprechen. Sie sind aus Wien, nicht wahr?
ja,
Marlene.
Nicky.
And it continues playing. So not only can we match a certain song, we can also match where in the song we are matching, which is pretty cool. So far the demos. Other things we could do with this idea was, for example, we could use this to detect duplicate songs. I did this with my old MP3 library, and I noticed there were a couple of songs that I had on multiple albums or live versions of songs. This works perfectly. You can totally use this algorithm to detect duplicate songs. Another idea I had was, what if we could use sound to align subtitles? For example, when you have a movie, you download an SRT file, and an SRT file is nothing else than just the text in the MP3 file, the text in the subtitle file with a certain point in time, which is a timestamp. But if the movie you're watching has like broken subtitles, maybe they're a couple of minutes off, it cannot correct itself. But if you would base the subtitles on audio fingerprints, it would always work perfectly. Even if your movie starts with a couple of minutes later or a couple of seconds later, it would align itself according to the audio, which is what we need. Could work. Haven't done this yet, but could totally work. This algorithm, this fingerprinting, is also used for copyright infringement. I'm pretty sure YouTube is using a similar algorithm to detect copyright infringement in videos, for example. Could this be used for speech recognition? Well, no, not really. It's just very different because now we are matching against a known audio piece and it has to be perfectly the same. In speech recognition, it works in a completely different way, so that's not very useful. So, end of day 2, end of my long weekend of discovery. Small recap. You can use fingerprinting to match. Using hashes is super fast. Shazam and SoundHound are very cool, but it's not impossible to make something like this in a weekend. There is a lot of room for improvement. My algorithm is far from perfect. I'm pretty sure if the library becomes too large, and there's a lot of things we could do better, but hey, it's working. At the end of the day, I had a working music matcher and I knew how this stuff worked. So now will be the time for questions, but I'm not here, so you can ask questions on Twitter. If you have questions about this, send me a tweet, send me an email, give me a call, drop by my house, I'm here. Thanks for watching.